Hi, welcome back to My Smart Learning. This is your physics lesson. It's for year 9s and 10 in particular, looking at efficiency, but it's useful for year 7s as well, because year 7s you do the energy topic, so you still need to know this in year 7. But again, it's revision. It comes up in the chapter 1 topic on energy, because you need to know about efficiency, and it also comes up in chapter 4/5 when you're looking at electricity, electrical circuits and efficiency for them. That's why I've posted it on Show My Homework for year 7s, I've posted it for year 9s, and I've posted it for year 10s. So it doesn't matter whether you're doing trilogy or separates, this is useful for both because you need to know it for all of them. So we're looking at efficiency today. Before we start, so the learning objective, how efficient is my appliance? How do I work out the efficiency of my appliance? And what is efficiency? Well, it's all to do with, before we go on to that actually, we'll do a quick recall quiz, our high five. You get all 5 right, you get a virtual high five from me. You can't even buy those in the shop, especially if you're social distancing. Now, question 1 then, what is power? Is what we did last lesson. Question 2, there's 3 formulae for power. So number 2 is power equals, number 3 is power equals, and number 4 is power equals. And number 5, what is the unit of power? So pause the video, quickly fill those in, and once you're ready, you can unpause and we'll go through these now. So what is power? Power is the amount of energy you use per second. So it's the amount of energy that is transferred per second. 3 formulae, don't matter which way around, but the way we did it last lesson, we did first, power is the energy divided by the time. So P equals E divided by T, PET. Power equals energy divided by time. The second one we did was about electrical circuits, and it was power equals current times voltage. P equals IV, I call it PIV, P equals IV. And then the last one we did was power equals I squared R, I times R. So power is the current squared times the resistance. So the last two were just to do electrical circuits. The first one is to power when we're talking about forces and we're talking about energy. And what is the unit of power? Is not a question, it's a statement, because what is the unit of power? Watts, but not with the H obviously, W-A-T-T-S, named after James Watt, our famous Birmingham engineer. Well, he's originally from Scotland, by the way, but he's Brummie true and true, because Industrial Revolution, James Watt and Matthew Boulton, so that's where the name Watt comes from, the unit of power. So, efficiency, what is efficiency? Efficiency of a device is how much energy is actually used by that device compared to how much is actually wasted. If you think back to the beginning of the energy topic, we talked about energy cannot be created, it can't be destroyed, it keeps changing from one form to another. So energy doesn't appear from nowhere, it doesn't just disappear. Well, what it does do is it keeps changing from one form to another. Now that form might be useful in your appliance, or it might be completely wasted. So for instance, my TV here, the useful energy is the light that's coming from it. The useful energy is the sound when I'm listening to the movie, right? But what's not useful, if I go near it, I can feel the heat coming from that screen. That's not useful. The TV isn't designed to warm up my room. It's not a radiator, it's just there to watch. But the heat is wasted energy. Efficiency is all about how much useful energy is there compared to the amount of wasted energy. So, the greater the useful energy compared to the wasted, the more efficient the appliance is. So that's the old-fashioned light bulbs. They're very inefficient, whereas those ones are more efficient. So when you look at appliances, especially your white goods, which by white goods I mean buy things you buy for the kitchen, like your fridge, your washing machine, your tumble dryer, dishwasher, those kind of things, you usually find these stickers stuck to the side of them. So next time you visit a shop like Curry's or whatever, there are other shops available, you can go and look at all the fridges and stuff, and you'll see these stickers on the side, and you'll see what kind of energy rating they have. So A being the most efficient, and if you go down to G, that would be the least efficient. So for instance, my washing machine, I want it to use electrical energy that's going in to spin, so it needs kinetic energy. It needs to get warm because I need to warm the water so that there's hot water inside of it. I also need it to obviously spin, so it needs kinetic energy and it needs heat energy. What I don't want my washing machine to do is make noise. That noise is a waste of energy, and that's happening because of the friction. When the drum is spinning around, there'll be some vibrations. So you want to basically make sure that there's no friction and therefore there'll be less noise. So you can see there it mentions the amount of noise that they produce, and it talks about how energy efficient it is and how much it will cost you per year to run. So that's what efficiency is all about. How do I calculate efficiency? Well, efficiency is the measure of how much useful energy you get out of an object compared to the total energy. So efficiency is the useful energy given out, what's useful, divided by the total energy that you put into it times 100. So you can also do this in the electricity topic for year 10s. You get another formula that looks very similar to this. Efficiency equals, it'll have the power output divided by the power input. It's exactly the same idea. Output divided by what you put in, power output divided by power input. Now the answer to that will give you as a decimal place, it'll be a decimal, it'll be somewhere between 0 and 1. 1 being like 100%, 0 being 0%. So it'll always be a number between there, like 0.84, which is like 84% or something. Now to turn that decimalised into a percentage, you always just times it by 100 to turn it into a percent. And remember, this number has to always be bigger than that number, because you can't magic up more energy than you've actually put in. So you'll know if you got it wrong if you get an answer greater than 100%. So always make sure that the big number goes at the bottom, the smaller number goes at the top. Okay, so the useful divided by the total energy that's gone into it times 100. Any waste energy from this causes inefficiency, and that's not what you want. So let's have a go at some questions then. Here is a TV. I've got 200 joules of electrical energy going into my TV, and I've got light energy coming out, because obviously I can see it, there's 80 joules. I've got sound energy coming out, because you can hear it, it's 40 joules. How much heat energy would I have coming out of my TV? I can feel it. Well, remember, what goes in must come out. It has to be balanced. Remember the law of the conservation of energy. Energy cannot be created, it can't be destroyed. It just changes from one form to another form. It can't disappear. So this has to add up to these. So 80 plus 40 is 120. So this number must be 200. Take away the 120, leaves me with 80. So 80 joules of energy would be for my heat energy here. Now, remember, efficiency is useful energy out divided by the energy in, times by 100. So let's have a go at a question. So here's the question. Calculate the efficiency if 2000 joules of electrical energy are put into a kettle and 500 joules of heat energy is gained from it, as in the water's gained 500 joules of heat energy. Well, it'll be the useful, which is 500, divided by the total, which is 2000, times 100. So 500 divided by 2000 times 100 gives me the efficiency, which will equal, well, that's a quarter, so it will be 25%. So not very efficient. Okay, some questions then. Have a go at those questions. Pause the video, have a go at these 3 questions. I'll go through the answers in a moment. And then if you've had a go now and I've unpaused it, welcome back. So, how are you going to work out these questions here? So, 500 joules of electrical energy is put into a motor, and the motor converts it into 100 joules of movement energy. How efficient is it? Calculated already. Some of this you can do in your head. I think most of it you can do in your head. But for your physics exams or any science exams, always have your calculators, because you need them for all science exams. Make sure you've got them. Okay, make sure that you've got, solar power battery working in them. So with this one then, efficiency is useful, which is that 100. Remember, the small number goes on the top, the big number goes at the bottom. So it's 100 divided by 5,000 equals 1 over 50, which is 2%. I'm going to times it by 100, and it'll tell me it's 2%, because 1/50th is 2%. So that is 2% efficient, so that's not very good at all. What about my laptop then? Question 2. A laptop converts 400 joules of electrical energy into 240 joules of light and sound. Well, that's useful for my laptop. I want to see it, I want to hear it. What is its efficiency, and where does the rest of the energy go? So there's 2 parts to this question. So the efficiency, the useful divided by the total, so it's 240 divided by 400 equals, then times it by 100 to get my percentage, which is, I've divided by 100, 240 divided by 400, which equals 3/5, which is 60%. Then you times it by 100 equals 60, because 0.6. So 0.6 times 100, 60% efficient. A bit better than that one over there. So 40% of the energy is wasted. Where's it going? It's going as heat energy, but where is it going? It's going into its surroundings. It's dissipating and spreading out throughout the surroundings. Okay, the last question then, a steam engine is 50% efficient, which means it's wasting 50%. 50% is useful, 50% is wasted. If it delivers 20,000 joules of movement energy, how much chemical energy was put into it? Well, that's the input. The chemical energy has gone in, so that's 100% of it. Now 50% of it is actually gone as movement energy. Okay, that means the other 50%, which must be another 20,000, must be the wasted. So the total, it will be the useful and the wasted together, which is going to be 20,000 plus another 20,000, which will give you 40,000. So it's 40,000 joules of chemical energy was put into that. Now that's a simple one because it's giving me 50%. This one, you'd have to rearrange the equation because you've got the efficiency is useful divided by total. Now the efficiency is 0.5 because that 50%, if you don't do it as a percentage, it's the decimal, it's 0.5. So if you've got 0.5 on that side and you've got something over something, so what it delivers is 20,000 is what is useful. You're trying to find out how much energy was put in, which is the bottom number. So you literally would swap those two numbers around. So you move the bottom number, the total energy, to the top, and you move the 0.5 to the bottom, so it becomes 20,000 divided by 0.5. Now if you divide something by 0.5, so 20,000, if you divide something by 0.5, you're actually timesing it by 2. But just to prove a point, divided by 0.5, divided by half. If you divide something by half, you actually times it by 2, and you get 40,000 joules. Okay, so that's efficiency. Now, to take it up a notch, so you need to be able to calculate those kind of things, we're going to look at something called Sankey diagrams. Now, a Sankey diagram is a way of representing graphically and using scale drawings of how much energy is going in and coming out. So this is electrical input, the energy input. And if you draw on graph paper, you can see that the width of this is 10 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 rows going that way. And if there's 100 joules going in, that means each row must be 10, because 100 divided by 10 equals 10. So each row is 10 joules of energy. Now, the energy output then, 20 joules goes as light. So I'm using 20 joules as light energy, and then the rest of it is wasted. The waste has gone out of its bottom, literally. The waste always goes down. It's going down the bottom. If you got 20 useful, well, 100 take away 20, the wasted is 80 joule is wasted as heat, and it goes into the surroundings. Okay? Now, how do you draw Sankey diagrams? You have to draw them to scale. So this is called a Sankey diagram, as in S-A-N-K-E-Y, it's one word, Sankey. Sankey diagrams, that is a Sankey diagram. So you draw it on a graph paper, you make sure you've got 10 rows to make 100, so each one is 10. So if I want to draw 20 coming out this side, I need to show it as 2 rows of boxes. So it's the width of it, not counting this way. The mistake people make is they're counting the number of boxes inside that coloured blue colour. They're counting the number of boxes. That's not 100 boxes. What that's showing is the width. The width of that, each row is worth 10. So that's 10 and that's 10. So that's why it's 20. The width of this is the direction of the arrow. So the arrow is going down, so the width is this way, going down. So how many rows have I got going downwards? It's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 rows. Each row is worth 10. So 8 times 10 is 80. So you've got 8 rows going that way, 80 joules. You've got 20 joules going that way. That's known as a Sankey diagram. It's another way of representing or showing efficiency. Okay, some questions for you. Another example question. I've got 20,000 joules per second there, 20,000 joules per second, which is 20,000 watts, 20 kilowatts of electrical energy going in. Got 4,000 going that way. Okay, it's wasted heat energy. I got sound energy going that way, 6,000. Well, how much is going to heat the water? Well, you can easily do it just by counting them up, by saying, look, 6,000 plus 4,000 is 10,000. So 10,000's gone there, which means 20,000 take away 10,000, that must be 10,000, right? So you've got 10,000 left. However, another way of doing it is counting the number of rows. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 rows there and it's worth 20,000. So if I divide that by 10, take off a 0, each row is worth 2,000. So how many rows do I have that way? You've got 1, 2, so 2 plus 2 is 4, 4,000. This way I've got 3 rows, 2, 4, 6, 6,000. So this one must be 2, 4, 6, 8, 10, because each row is worth 2,000. So it's 5 rows times 2, it's going to be 10,000. So that's going to be 10,000 gone to heat the water. Here's another one. How much energy is converted into useful energy? So, well, there's numbers missing here. Something's been covered up. So I've got 150 joules there. I've got 20 joules of wasted energy here as heat. I've got 150 gone that way. And let's say I've got 30 joules of converted into useful energy. So if that's the wasted, then what's left is 130. So this will be the light and this will be the sound. So how efficient is it? So I know that 20 is wasted. So 150, take away 20, 130. So these two add up to 130. They're the 130 useful energy. How efficient is it then? The laptop's going to be 130 divided by 150, because that's what's useful. 130 is useful. 150 was the total going in, equals that. Times it by 100 gives me 86.6 recurring efficiency. So that's what, if I round it up, 86.7%. If I just round it to a whole number, 87% efficient. Okay, because it's the useful, which is 130 divided by the total, which is 150, gives me the efficiency. So that's what I'm teaching you today about efficiency. On the Caboodle textbook, on the PowerPoint, I've given you the questions on there, so you can have a go at that. Look like that, and there's some more there. So there's more example questions, there's some key points for you to get down. To finish off, we'll just have a quick quiz. Let's start here, efficiency. Here is a car engine, it's 25% efficient. How much input energy produces 100 joules of useful energy? So a car engine is 25% efficient. How much input energy produces 100 joules of 100 joules of useful energy? If it's 25% efficient, that means it's going to be making, if you're getting 100 joules, you're going to be getting 4 times as much as that, because 25% is a quarter. So you're going to be getting 400 joules of energy going into it. Okay? Because you're going to do 100 divided by your 0.25, because that's your 25%. Okay? So there's a few of these kind of questions for you to have a go at on the PowerPoint that I've sent. You need to open it on the old format of PowerPoint if you've got the old 2007 version, because some of the flash animations don't work on the new PowerPoint systems. But there's some questions for you to have a go at. There's 10 questions here, so you can assess yourself. If you've learned then about efficiency and it's been useful for you, please watch the videos, like the videos, share the videos and subscribe if you haven't done so already. And I'll see you guys next week. So this week we've looked at power, the 3 equations for power, and we've looked at efficiency, how efficient, how you do the calculation for efficiency, what efficiency is, and how you calculate it for different appliances. Next week we're going to go on to some other bits and pieces. So I hope that's been useful. Please keep watching them and keep safe, and I'll see you next time. Remember, if you got all 5 right, you get your virtual high five from me.